Hello, this is the second part of chapter 11, and in this video we will talk about SN1, that is substitution nucleophilic unimolecular reaction. Okay, but before we do that, let's quickly review what we studied in the previous section. We had talked about SN2 reactions, where the factors which affect or which increase the rate of the reaction would be if we have a methyl or a primary substrate. Okay, so we prefer either like a CH3Cl or like a primary alkyl halide, which is good substrate for SN2 reaction. A nucleophile which is strong, like negatively charged. So that's a preferred nucleophile for SN2 reaction. So examples are like OH minus or SH minus. We have the alkoxide like CH3O minus. So these are examples of strong nucleophiles. Then regarding the leaving group, we talked about groups that can be stabilized in their anionic form. So halogens, like halides, are all good leaving groups, and among the halides, iodide, which is the largest one in size, is the easiest one to leave. Then it is the bromide, then the chloride, and then the iodide. Okay? And fluoride. And then better than the halogens are the tosylates. If you remember, tosylates are one of the most one of the best leaving groups. However, we are talking about alkyl halides, so among the alkyl halides, iodide is the best leaving group. Okay, and then finally we talked about solvents, and the best solvent to use for an SN2 reactions are the polar aphotic solvents. That means the solvents which do not contain NH or OH type of bonds. Okay, so we do not want these kind of bonds, so we prefer solvents like acetonitrile, CH3CN, or we have the acetone. That's another good solvent. DMSO. These are all good solvents which do not have the Now we are going to talk about SN1 reactions. Now, in terms of reactivity, the SN1 reactions have an opposite trend for the substrate. That means the most reactive substrates for an SN1 reactions are the tertiary alkyl halides, then comes the secondary, then comes the primary, and then comes from the methyl. So this is exactly opposite of what we had seen in SN2 reactions. So for example, if you take an alkyl halide and react it with a nucleophile like water, which is kind of a medium or a weak nucleophile, okay, unlike OH minus, which was a strong nucleophile. So in SN2 we had strong nucleophiles reacting with alkyl halides, and now this one, water, is actually a medium nucleophile which is reacting with an alkyl halide, and you can see that the Br is replaced by OH here from the water molecule. However, the reactivity for this reaction, tertiary alkyl halides would work the best, and the methyl alkyl halides would work the least. Okay, so this means that the mechanism of this SN2 reactions is different from the SN1 reactions. And in SN2 reactions, if you recall, it was a concerted reaction. Everything was happening in a single step, where the leaving group was leaving, at the same time the nucleophile was attacking, and the transition state had a 5-membered state for the central carbon atom, which was the one that was attached to the halogen molecule. Now in this case, it's a 2-step reaction where the intermediate is actually a carbocation. Okay, so the first step would be the rate determining step, where the alkyl halide, which is my substrate, reacts with the nucleophile to form an intermediate carbocation, which then In the second step, the nucleophile, which is the new nucleophile that is attacking, will attack the carbocation and then form the product. So it is a two-step reaction, and the first step is the rate determining step, where the rate of the reaction depends only on the alkyl halide. The nucleophile does not appear in the first step. Okay, so if we write down the rate equation for an SN1 reaction, the rate equation would be rate equals to the rate constant K, depending only on the substrate, which is your alkyl halide, and not on the nucleophile. Okay. Also regarding stereochemistry, the SN1 reaction produces racemic mixture because the carbocation that is formed is planar structure, and the nucleophile in the second step can either attack from the front side or from the back side with equal probability, and so you get 50% inversion of configuration and 50% retention of configuration, giving us a racemic mixture. Okay, so here is another example of an SN1 reaction. You can see that it's a chiral center and it's a tertiary alkyl halide, which would be the best substrate for an SN1. Water is taken as the nucleophile, and you can see that about 60% is S configuration and 40% is R configuration. Okay, so it's not exactly a racemic mixture, but you get both the configurations in the product. Even benzylic and allylic carbocations can undergo SN1 reactions. The allylic and benzylic carbocations are very stable because of the fact that they can undergo resonance. So their reactivity is almost similar to a secondary carbocation. So we can see similar reactivity of allyl and benzyl carbocations to secondary carbocations. So here is the reactivity trend of different carbocations for an SN1 reaction. Methyl is the worst, tertiary is the best, and in between we have primary, allylic, which is kind of similar to benzylic, which is again similar to secondary. Okay, we have examples of allylic and benzylic substrates, and you can see that the in case of an allylic alkyl halide, the carbon halogen bond is around 289 kilojoules per mole, and then the carbon halogen bond in a benzylic is about 293. They both are lower than a primary alkyl halide, right? So it's more easier to break these bonds than in case of a primary alkyl halide. Okay, okay, so before that, let's summarize what we learned so far regarding the mechanism of SN1 reaction. So here we have SN1 mechanism. Okay, SN1 reaction mechanism. Let's take an example of a tertiary alkyl halide, because this is the best substrate for a SN1 reaction. So the tertiary alkyl halide reacting with water molecule. Let's do water because that was the example we saw before. The first step would be the overall reaction. Let's write down the overall reaction first. The product produces a OH alcohol and HCl as your side product. So in this case, the first step would be formation of the carbocation. So for that, the chloride would leave and you get a carbocation, which is a tertiary carbocation, which is the most stable one, and then chloride is removed, negatively charged. The next step, the carbocation is attacked by this nucleophile, which is the water molecule, which is my nucleophile here. Now, water molecule attacks as a whole through its oxygen atom. So we can write down the intermediate, which looks like this, O, H, and H with a positive charge on oxygen. Okay. Now the chloride, which was removed in my first step, that's going to act as a base, remove the proton, put the electrons back here, and the final product would be the alcohol. Okay. So this is the mechanism of the reaction, a two-step mechanism. The first step is my rate determining step, and that's my slow step. and this is the step that determines the rate equation. So rate depends only on the substrate, which is my tertiary alkyl halide. Okay, so the rate is depending only on the concentration of the alkyl halide, because the nucleophile does not appear in the first equation. It actually comes in the second equation. See, this is my nucleophile and it comes in the second part of the step. However, the first step does not involve nucleophile, therefore the rate depends only on the substrate. That is why it is called as the SN1, where 1 stands for unimolecular. It depends only on the substrate. Now regarding the leaving group tendency, it's the same as SN2. That means if you have a good leaving group, the reaction takes place faster. OH minus is the worst leaving group, and the tosylate or water molecule, these are the best leaving groups. Okay, and then among halogens, iodide is the best leaving group, and then chloride would be the worst leaving group. Okay. This is kind of the same trend that we saw in SN2 reaction. So here again, it's showing the mechanism of SN1 reaction. We already looked at that. Now nucleophile, since it does not appear in the rate equation, you can either use strong, weak, or medium. It doesn't matter. Generally, a weak or a medium nucleophile works good for an SN1 reaction. Okay. Regarding solvents, here we prefer polar protic solvents. Okay, unlike in case of SN2, where polar aprotic solvents were preferred, here polar protic solvents help to stabilize the intermediate carbocation by solvating it. Okay, so if you have polar protic solvents like water or methanol, they can orient around the positively charged carbocation, and then they can stabilize it. So we prefer polar protic solvents. Okay. So that's different from SN2 reactions. So here we can see that the reaction with alcohol for a tertiary alkyl halide, if you use ethanol, the reactivity is the most, and if you as the polar protic solvent part increases, then you can see the reactivity goes on increasing. So as you add water, which is polar protic, you can see the reactivity goes on increasing. Here is now you are ready to solve questions where you may be able to predict whether the reaction proceeds through SN1 or SN2. So the first thing in a question like this would be to check out what kind of substrate you have. Okay, so here we have a secondary alkyl halide or a benzylic, right? We can say that benzylic and secondary, they are kind of similar, right? They both are close to, their reactivity is close to each other. So it's a benzylic alkyl halide, and benzylic halide, and then it is reacting with an acetate. So this is your nucleophile, which is negatively charged, right? And then we have acetic acid and water, right? Now this is a medium nucleophile, and then also the presence of polar protic solvent tells us that this reaction should be an SN1 type of reaction. Okay. Now the second one is a primary alkyl halide, which kind of suggests that it may go through SN2. Here again, look, this is a strong nucleophile. Okay, it's a strong nucleophile, and also this is a polar aprotic solvents. So this all tells us that the Br is replaced by the nucleophile, which is OCH3, and it should be a SN2 type of reaction. Okay, so it's the answers are given here. It's telling us that the SN1 reactions are more better if we have an allylic or benzylic substrates, and then non-basic nucleophiles and by protic solvents. So they all suggest that the equation 1, which we saw before, is then SN1, and then the second one is an SN2 reaction. Now we can talk about elimination reaction in the next chapter or the next video.